Okay. And by the way, the slides for midterm review are up on the website also. Okay, Facts and Fallacies. Great book. Keep your copy. Trust me, you will be running into this stuff constantly. Maintenance. It's actually at the end of chapter 2. Within organizations, and frankly, within businesses that sell software, maintenance of existing systems consumes the vast majority of the IT budget. In other words, other than in a startup where you're creating a new product for the first time, in most cases what you're doing is there are existing systems that you're working on and you're being asked to do one of two things. Fix bugs or add features. Most software lives for a long time, very long time. Within organizations, commercial software, I have been using Microsoft Word for over 30 years. I was a bit slow to change because I was used to several of the word processors of that era. WordStar in particular was sort of the dominant one. But I helped to write the first embedded spell checker for a commercial PC word processor. I worked for a company called Oasis Systems, same place I did Sundog Frozen Legacy. We also did word processing tools. We had a standalone spell checker, which was all that spell checkers were back then. And Microsoft wanted one to put into Microsoft Word, so they sent us their file specification. And Wayne Holder and I spent days pouring through it, trying to interpret it, and figuring out how to take our spell check technology and make it interact within the Word file format, which is largely a thing here. Old hardware becomes obsolete. Old software goes into production every night. Oh, this is so true. Now, in a way, you're sort of fortunate. There was a great firestorm because of Y2K. Lots of old production systems that companies have been unable to get rid of for years. They used Y2Ks exist as a excuse to burn them to the ground, replace them wholesale. It actually caused, the tech crash that happened in 2000, which is sort of sad. You guys were kindergarten. I still feel the pain from that. Happened in part because here in the U.S. we spent $100 billion on Y2K remediation. And basically the corporations, from large down to mid-sized and even small, blew their IT budget for a couple of years on making sure all their systems were Y2K compliant. And so once the deadline passed and they fixed the last remaining bugs, they basically didn't spend anything for a couple of years. Yeah, the dot-com crash happened at the same time. It was just pretty ugly in the IT industry. I say 50 to 80%. I've seen organizations that were on track to consume 100% of their IT budget on maintenance if they didn't do something. So you're going to run, for those of you who go into corporate or organizational settings, you're going to see this as a real issue. For those of you who go to work for companies that produce products, maintenance is in effect simply doing the next version of your product. Some of you may get to do a new product from scratch. That happens, that's great fun and so on, but recognize that maintenance is going to be a lot of what you're going to do, which also means you're going to be spending a lot of time learning other people's code. Enhancement represents 60% of maintenance costs. Now, there's usually what they want to do with existing systems is we want to make it better. So 60% of an IT budget is maintenance, 60% of that is enhancement. Therefore, roughly 40% of an organization's IT budget is enhancing old systems. less to spend on fixing bugs. You have adaptive maintenance, which is saying, you know, we have this application, it's running on Windows XP, we have to move it to Windows 10, that kind of stuff. And a sad tiny fraction is paying down technical debt. It's like, we did this quick and dirty. Now we need to go back and do it right. It is very hard to get management to agree to spend time and money doing that, because they say, well, what are we gaining? Well, we're gaining benefits in the future because we'll be able to make enhancements faster, we'll be able to fix bugs faster. No, just do what we ask and make it work somehow. Maintenance, like QA, is sort of a second-class citizen. Yet it's the single most important source of IT spending within an organization typically. In fact, I would probably say well over half, maybe 75% of the failed IT project cases I take on as an expert witness are cases where management decided to replace their existing legacy system with a new system. Rather than maintain the old one, they wanted to go with something new. And often they end up spending money if the project fails. Well, I literally was just reading a deposition in a system failure case I'm working on, like that. And the person being deposed is the chief operating officer of the customer's company. And they spent a couple of $1 million trying to get a new and improved version of software to replace their legacy system. Project failed. They finally went on a stop order, and he mentions this deposition that he did just a few months ago. Said, we're still running on the old system. Often you can just continue to run on the old system. You want to think carefully about, you want to count the cost carefully before you do it. Here's something else that's overlooked with maintenance. Maintaining a product, which means either enhancing it or fixing bugs, but mostly enhancing it, involves the full software development lifecycle. You have analysis. You have to review architecture and design to see what changes need to be made. You have implementation. You have quality assurance. The problem is you're not starting from scratch, so you also have to understand the current system. And what you'll find in organizations is that either there's no one who really fully understands the current system. This is especially true in military and government systems. There's these vast systems that no one really understands anymore. And they sort of, keep it functioning with the IT equivalent of chewing gum and baling wire. Or the people who understand it are some of your lesser lights in your IT department who have found a safe position because they're the only one who understands the system. So they may not necessarily be the best software engineers you have in the group, but they know how the system works. And so they've sort of got a job for life unless you replace it. Part of the problem here is that maintenance is actually more difficult than development because you're constrained by the existing system and all the baggage it brings with it. It's one of the reasons why companies are often so tempted to replace legacy systems with a brand new from scratch system or modified off-the-shelf software. But unless you fully understand the existing system, your new solution may not work properly. Yes?
So in this situation, would you say things might be different for a company that uses a microservice architecture, where lots of people might understand each individual microservice, but no one has an idea of maybe how the entire thing works together? or is it a different scenario where that doesn't matter?
Well, actually, the microservice is nice because you sort of, instead of big chunks that you maintain, you have lots of little small chunks you maintain, which means it's easier to replace, upgrade, enhance each of those. It's easier to understand each of those. It's basically managing complexity by decomposition. But if the applications that are using the microsystems are still big, monolithic, and aging systems that have simply had portions carved out and replaced with a microservice, you still need to understand the architecture and design of that big system. It does make your job easier. I mean, there are things you can do to make maintenance easier, like have a good orthogonal architecture with chunks that are relatively independent of each other and that work together so you can make changes into one without, having things that ripple throughout the other. But when you have hastily done IT, you tend to get quick and dirty patches and solutions. So you're sort of running tubes from place to place. And when you go to update it, you suddenly discover you've got like half a dozen connections between major subsystems that don't seem to be related. And as you try to change one, it starts affecting behavior elsewhere. Better software engineer leads to more maintenance. Why?
As they're going to continue getting better, and they're going to look at their old code and say, I know how to make this better.
There you go. Right there. The better it's designed and built, the longer it stay in production, the easier it is to modify. Therefore, a well-designed and well-built system will require more maintenance in terms of having a longer lifestyle and probably be enhanced more because you can enhance it. And they come back and say, we need to add this. Like, oh yeah, we can add that feature. This, by the way, may I add, is on a sliding scale. This is one of the great mistakes we make as engineers. And mistake in terms of conveying what we're doing to non-technical management. You're working on a system and management or marketing comes up and says, could we add this feature? And immediately you can see, oh yeah, this is all it requires. And you say, yeah, we can add that. And you go, and the next day it's like, bam, it works. And they become very impressed. And then they come up with a feature that you can't do like that, and they think you're stonewalling. This is back to my story at Pages with the rotating headlines. Larry says, why can't you put in rotating headlines? Like, Larry, we explicitly planned against that. And given our current time pressures and the fact that we're still trying to ship, no, it would require breaking a lot of stuff. How many of you have had the experience of working in a program and you think of a feature or someone else suggests a feature and you're able to add it almost immediately? It's fun. That's great. It's like, oh man, I do this and bam, this happens, and I do this and this happens. But in your mind, you always have this set of, here are things that I can do very easily, and here are things that would be a royal pain in the butt. And it's good to proactively educate management as to which are which. And try to devise categories. Say, well, here are things that we could do that would be very simple. These other things are going to be far more difficult. Okay, quality. Robert Glass, bless his heart, is a little incoherent at times on quality. He says quality is a selection of attributes, and he has his list, I have my list. And he includes reliability. Then in his very next fact, he says reliability is not quality. Anyway, the ones I like are reliability, performance, functionality, compatibility, lifespan, deployment, support, cost. And we'll talk about these in a separate lecture. The best definition of quality I like is one that comes from Jerry Weinberg, who's probably written more on software quality than anyone else, which is quality is value to some person. The problem you come up with, getting back to negotiations and love songs, is that the value varies whether you're talking about programmers, marketing types, end users. What they want is not necessarily what you want. And what marketing wants isn't necessarily what the customers want. I was just talking to someone who was beating his head against the wall working for a software firm here in Silicon Slopes, where their new CEO has said, I don't care how bad the software works, I want it to look good. That's a great way to alienate customers. You know, I'm a firm believer in you know, user interface, user experience, and so on, but customers are very unforgiving of serious defects. I'd rather have something that looks a bit uglier and more awkward and works perfectly than something that lies to me with a pretty face. There are errors that most programmers tend to make. This is true. How many of you have ever done if A is assigned B in a programming language? Yeah. Probably more than once. It's like, oh, well, I can't believe I did that again. There is a mantra in open source software that said, given enough eyes, all bugs are shallow. Empirical tests have shown, and it actually talks about this. Empirical analysis has shown that's not true. Because with enough eyes, we all still overlook the same bugs. Or we figure out other people are looking at it, and we don't dive down to figure out what's there. This is interesting. Errors tend to cluster. He's basing this on studies that, again, how many of you have worked on systems that are sufficiently large and complex that you've got, it's more than a simple program, and you notice that problems keep cropping up in one particular portion of the code. How many of you have had that experience? Yeah. My personal feeling is this gets back to the deferring hard problems. That the sections of code where that happens is one where hard problems exist and either haven't been identified or they've sort of been pushed off. You've gotten an 80% solution, and once everything else is working, that other 20% is like a nail embedded in your tire that just keeps leaking things. There's no single best approach to error removal. It's sort of like this, the stop and think about it. If we could truly train computers, develop AI that would program as well as humans do, then the AI should also be able to do software quality assurance as well as humans do. My experience with many years of finding bugs in my code and other people's bugs, in other people's code, and finding other people's bugs in their code, is that it often requires bringing a whole number of different approaches to bear until you finally isolate down on something and say, oh, now I understand what's happening there. Again, given the vast state space that exists within software, there are bugs that can live there for a long time. Residual errors will always persist. What you want to do is to minimize or eliminate the severe errors. This is why you do prioritization of errors, both in terms of how severe the impact is and what's the likelihood of it being encountered. It can be hard to ship products with bugs in it, but guess what? We all do it. Sometimes knowingly, sometimes not. But if you're doing commercial software, a lot of defect management is deferring bugs. We'll fix that in 1.1 or 2.0. Getting it out there. Okay, efficiency. John Knuth's fond of saying that premature code optimization is the root of all evil. There is a back and forth swing on the issue of optimization. There's a school that says get it right and then make it fast. The problem with that school is sometimes in getting it right, you encode a solution that blocks making it fast. And therefore you have to go back, and now that you know how to do it right, you say, how do we design this? But efficiency is something you need to address very early on. If you have performance requirements, if you know you're doing transactions at the rate of 10 records a second, it's kind of like, okay, well, we can do this. If you're doing transactions at the rate of 1 million records a second, you're going to need to think very carefully about your software and hardware architecture and what's going to be required in order to do that. He talks about higher order languages versus assembler. That's not much of a debate anymore. Actually, over the last 20 years, it's more compiled languages versus bytecode languages. Then you have just-in-time compilers and so on and so forth. Trade-offs between size and time optimization. This is classic. Of course, this was a very big deal back when memory was very constrained. Doing sendog, I needed trigonometric functions. Doing an 8-bit integer processor, so I do lookup tables. And I only need resolution within about 15 degrees, so it's very simple lookup tables for sine and cosine on 15-degree increments. Now, you don't have to worry about stuff like that these days, but my observation is a lot of modern software is sloppy both in memory usage and in performance. It uses a lot of memory without really gaining the performance gain that it should from it. Yes?
As an example of that, I used to use Atom, which is a popular text editor now. It would often use like 2 to 3 gigabytes of storage. I just had a couple of windows open with code.
Yeah.
No graphics, no weird stuff. It's just text.
And you don't know if that's sloppiness or really bad memory leak. But yeah, I won't go back to back when we counted our bytes, though I have counted bytes. But there is a lot of software bloat that is based not on carefully considered performance trade-offs, but frankly laziness. Well, of course we're going to require 16 gigs on a laptop like mine. And of course, memory keeps expanding. My son runs the lab for I say IT department, you think, oh, the computers. No, it's the department that teaches IT, teaches network management, security, system administration over in the Crab Tree building. He basically runs the whole lab floor. He has a server there with 1.5 terabytes of RAM in it. He showed that to me. I thought that is so cool. So I had a personal goal that I set about 25 years ago, which was to have a home system that had 1 terabyte of storage in it. Which, of course, nowadays is like, what's that, flash drive? I achieved that about 14, 15 years ago with the desktop system I had in DC. Had 3 drives in it, and it was 1 terabyte. Okay. My new goal within my lifetime is to have a single system sitting on my desk that's got a petabyte of storage in it and a terabyte of RAM. At current rates, it should be about 10 years. In about 10 years, I should be able to put that together.
We are having some difficulties with literal quantum physics getting in the way.
But we are getting this. I just saw Samsung's got a 340 terabyte SSD drive?
I think so, but it's not normal.
Well, no, I know it's not normal. But like I said,
you couldn't put it in your laptop.
Like I said, I'm looking 10 years down the road. I'm amused because for 40 years I've been seeing articles that come out and say, we finally concluded on Moore's law.
Yeah.
And then 2 years later it's like, oh, we just made a new breakthrough on this. And
there's always going to be some sort of engineering method.
Yep.
Like, are they going to have to stack CPUs at some point?
Yep.
How do you pull them? And
Well, I actually have seen that hit with processors. It used to be, you know, okay, we're increasing the bit width of the processors, we're increasing the clock rate, and it finally got to the point where heat and RF radiation became major problems. So it's like, okay, we're not making the processors really any faster, but by golly, we're adding lots of cores.
well, and they're also really, really working on optimization of like aggressive optimization and branch prediction and stuff.
Yep.
Like without any of that, it'd be so much slower.
On the other hand, meltdown and Spectre are tied to
Oh
some,
yeah,
of
we'll talk directly to that.
some of the problems with the processors there. Okay, research. Most software researchers advocate rather than investigate. Now this is actually why Glass's book is so valuable. For most of his chapters, he has actual citations. What you'll hear is, oh yes, we should do this. The question is, okay, does that really work? Are there any studies that show that this actually does benefits? He says a lot of received wisdom is based on common sense or wishful thinking. Okay, so that's the end of his facts. His 55 facts. Now he's got like 10 fallacies. See, look at this. We're gonna be in pretty soon. I have to take roll. We've got a couple announcements, so don't jump up and run away. But we're not going to have a break today because we're going to finish this up probably in the next 15, 20 minutes. Fallacy, you can't management. Okay. That's probably been there for 3 semesters now. Can't. I'm correcting it right now, so I don't do this next semester or this fall. You can't manage what you can't measure. Yes, you can. We do it all the time. And in fact, this is the book that I held up a few weeks ago, Measuring and Managing Performance in Organizations, which does pretty, in my opinion, is a pretty devastating critique of attempts to manage to specific metrics. Because when you manage to specific metrics, and as a silly example, you know, we want you to produce 10 lines of code per day. Stop and think of all the things that you just as soon as I said that, thought of ways to work around it. Well, I'll write 100 lines of code and I'll just, you know, put 10 in a day, and that way it's, by golly, I'm being productive day after day. That, on about every level, is what happens when you try to manage the metrics. It distorts your organization. Austin does a great job of saying, here is what you have to do, and it parallels what I said about project estimation metrics. You need things that are repeatable, objective, and automated. But even with those, there are things that can get fudged. You can manage quality into a software product. And this is in the sense of, you know, rah, where, you know, quality is job one. No. Quality requires a commitment to quality. Quality requires management being willing to address the full range of quality activities, not just testing, and making sure that products don't go out without quality. What I keep getting back from different, and you know, I have 2 different adult children working for 2 different software companies here in the area, and I have within the last month had reports from both of them of issues of their companies deliberately what's the word I'm looking for?
Sabotage.
Not sabotage, deliberately saying, no, don't worry about this quality. And we're not talking about, like, you know, going to 5 nines or something. We're talking about pretty basic stuff. Don't worry about this, we just want to push stuff out to the customer. And what my children are reporting back are basically customers are really ticked. I don't understand that mindset. It is short-sighted, and it always kills you. I thought someone were starting to comment. Okay. The quality depends upon the care, the skill, the intelligence of the engineers. And I would add the willingness of the management to allow you to build a quality product. You don't hear this much anymore. Way back, by the way, I highly recommend Psychology of Computer Programming. There's a 50th anniversary edition, originally published in '71. The technology examples will all be dated, but boy, Jerry Weinberg pretty much had it all nailed nearly almost 50 years ago, as far as interactions within a software development group and with developers. This is sort of a precursor to peopleware. But one of the things he touted in that book is programming should be egoless. If I write code, I should be able to put it out there and withstand whatever criticism I have from everyone else and so on. And the class says, well, yes and no, because part of quality is taking pride in your work. So in your coding, you need to be willing and be able to have other people frankly review your code and come up with critiques and not get upset about it, even if it's unfair. But you need to be invested, professionally and personally invested in your code. Okay, tools and techniques, one size fit all. This is pretty much, we're back to the, not just silver bullet, but the idea that any given tool, technique, methodology, or whatever works in all situations. A particular language, a particular engine, a particular methodology, a particular organizational technique that might work wonders for a small 5-person startup would likely fail miserably on a 200-person government software project. As always, people matter most, so what you want to do is get the best people and figure out what's going to work. Software needs more methodologies. We're sort of fortunate. We've sort of settled into a waterfall-ish versus agile-ish approach. And there are more people who are actually a bit more rigorous on agile. Everyone says, no, don't do waterfall, and yet I would say 90% of the world's software is actually done with basically a waterfall-like approach. But there was a time in the 80s and 90s when there were new software methodologies coming out. I mean, I have probably a couple dozen books on different software methodologies, including some books which are compendiums of methodologies. And they all pretty much went by the wayside. Fallacy 6, estimate cost and schedule first, estimate lines of code. Okay, we all know that's silly. Random test input is a good way to optimize testing. No. You're not doing infinite number of monkeys. You need to very carefully, because it's the way I think of it. And I'm going to do this very simple because your software state space doesn't look nearly as neat as a simple cube. But you have this cube where you have quintillions, septillions of different states that can exist. But if you think about it carefully and design your software carefully, you can identify the boundaries. Basically say, as long as the software state stays within this box, I'm happy. It's only when it starts to poke out on the sides that I'm dealing with combinations of values that I don't want. And so a lot of software testing says, okay, we want to define what the boundaries around the state space of the software are, and then focus our tests to make sure we're not violating those. We're happy if stuff stays in there. We want to see what happens when we start to get towards the boundaries, whether or not we're breaking any walls here. Which is a very, very crude and poor description of the lengthy paper I have by Bob Bender on software testing. We've talked about the given enough eyeballs, all bugs are shallow. Deep and subtle bugs remain deep and subtle regardless of how many people are looking at them. How many of you know about the problem with the number of human chromosomes? For many, many, many years, and I want to make sure I get this correctly, I keep from embarrassing myself because I'm trying to remember which way it went. There we go. Some of the earliest research in the number of human chromosomes based on microstructure is that there were 48 human chromosomes. And that's what was reported for decades and decades and decades. And then in 1956, someone looked more closely and said, I'm only counting 46 here, not 48. And everyone else looked and said, oh yeah, there's only 46 here, not 48. I'm old enough to have run across textbooks as a child that still referenced 48 chromosomes. So 1956, that someone finally said, you know, I'm not coming up with 48 here. I'm only coming up with 46. You have the same phenomenon with a lot of bugs are deep, subtle, and easy to overlook. And you can get everyone to look at them and no one will see it. How many of you have seen the basketball video? I'll spoil this for the rest of you who haven't. There's a basketball in which you're asked to count the number of times a group of people just casually bouncing and passing a basketball back and forth, and you're asked to count the number of times the basketball gets passed. And you watch it. At the end, you say, did you see the gorilla? In the middle of the video, a person in a gorilla suit walks right through everyone to the other side. Most people will not see the gorilla the first time they view the video. They're so focused on watching the basketball go back and forth and keeping mental track of it that they just completely blank out. In fact, someone in a gorilla suit just walked right through the middle of the film. There is a similar human blindness to a lot of defects.
That sounds like a good ADHD test, actually.
It could well be. Best way to predict future maintenance costs is to look at past cost data. Now, the cost data, this close, just easy out there, tends to focus on defects rather than enhancements. In other words, if I'm in an organization, I've got a system to say, you know, we're spending $10 million a year maintaining this one system. We're creating a new system. We figure that we're going to spend $10 million a year on it in maintenance. You really don't know that because maintenance costs are going to be based on mostly on enhancements being requested. So the question is, with the new system, how many enhancements are going to be requested? What's going to be the expenditure required for it, and is it really comparable to the existing system? You teach people how to program by showing them how to write programs. This is interesting. He contends that we should start by teaching people how to read code and then have them read it and test them on how well they understand it and discuss it. I would love to teach an introduction to programming class using this approach. To give people samples of good, solid production code, starting with simple samples, working more complex, saying, okay, here's how you interpret, have them discuss it, make sure they understand it, have them answer questions, and so on. And do that before they ever write any code of their own. Yes?
I think that's kind of the philosophy of the early CS internships for freshmen and sophomores. Because if you go into some company, you're going to have to deal with their legacy code and with the code that other people have. And you might not be a good programmer at the time because you're just learning.
Young, yeah.
But you will probably be a much better programmer than if you never did an internship like that.
Yeah. I think there's great value in reading code. Sometimes it's a warning because I've read an awful lot of bad code. On the other hand, I've read a lot of good code. And sometimes you read good code and you think, oh my gosh, that's a brilliant approach. That's great. And you mentally tuck away these little approaches and say, okay, next time I'm doing this, I'm going to do that. Yes?
I was going to say, I can testify that I initially learned how to program by being given a program and then asking to change it to do something slightly different.
Which is not a bad approach, as opposed to writing something. When you're coding for the very first time, it's kind of like, okay, I've got this editor, this IDE, and I've got these funny syntax issues, and I left off a brace or a semicolon here. What's wrong? I wrote, if A equals B instead of A equals B, all that sort of stuff. An approach where you are given working code and you're asked to make successive modifications, which I think there is actually a Parody O'Reilly book cover that I mentioned that says, how to learn programming by making small incremental changes to code that actually works. That's actually, particularly for a new system, new language, or so on. It's like, yeah, give me some working code that's using the API or working code in this language, and I'm going to keep just making little changes. And, oh, nope, that broke it. Oh, hey, that's working correctly. And that's the end of him. I've got to take roll.